Hello everyone, Dr. Ziaur Tahir here. This video tutorial is solution of problem 2.71 from chapter 2, free vibration of single degree of freedom system from the book Mechanical Vibration by S.S. Rao, 5th edition. So the statement of the problem is find the natural frequency of pendulum shown in figure 2.95 when the mass of the connecting bar is not negligible compared to the mass of pendulum bob. So here the mass of the connecting bar is given as m and mass of the bob is given as uppercase M. So to start with, I am going to draw its free body diagram. So the free body diagram here I have like here is the center of mass of rod and here is the center of mass of bob. So I am going to find natural frequency of uh, this system using Newton's second law of motion. So for undamped system, spring mass system in a translational spring mass system, its equation of motion will be mx double dot plus kx is equal to 0. So the natural frequency is whatever is the coefficient of displacement divided by the coefficient of acceleration. And when it is single degree of freedom system in a torsional system, so then equation of motion is j theta double dot plus kt theta equals 0. And then any the coefficient of theta divided by the coefficient of theta double dot, so that is natural frequency. So I'm going to solve this problem using Newton's second law of motion. So now the weight of the bob is acting downward and it makes angle theta with the rod, and weight of this connecting bar is also acting downward making an theta with the rod. And now uh, these two weight can be resolved into two component. One is in the direction of the along the rod, which is mg cosine theta, and the other one is mg sine theta. And similarly here I'll have a component as lowercase mg sine theta, and one component acting in this direction is lowercase mg cosine theta. So now in this case I have assumed the direction of motion, so that is the direction of motion in anti-clockwise direction, so that is theta and theta double dot. So here I can apply sum of moments. Sum of all moments is equal to equivalent j equivalent theta double dot. So now about this point of rotation, let's say this point, th this one about point O. So I can find moments due to these components of weights. Now uppercase mg cos theta, weight of the bob, component of the weight of the bob along the rod, and lowercase mg cosine theta, that is the weight of connecting bar. So both of these two are passing through the point of rotation, so they are not going to contribute towards any moment. And then this lowercase mg sine theta, this lowercase mg sine theta is acting at acting at somewhere that is distance L. Okay. So now due to here mg sine theta times by L over 2. So that is the moment which is opposite to the direction of motion. So it will be negative. So sigma m here it will become minus mg sine theta force times by radius of rotation L2. And the other one is minus again mg cosine theta into L and is equal to J equivalent theta double dot. So now this J equivalent is that is rotational inertia of connecting bar and then rotation inertia of the bob. But remember here, for small angles in radian, the sine theta is nearly equal to theta for small angles in radian. For small angles in radian, because here we are like the angle we are considering is a small angle in radians. So now I need to find that equivalent J equivalent for this whole system. And J equivalent for that formula for J equivalent is the moment of inertia of rod having a mass m and length L about its center is G. So Jg is 1/12 m over L squared. But this rod is not rotating about its center of rotation. It is rotating about something different. And then the moment of inertia of mass m having center of mass G rotating about point A, and the distance between A and G is D. So here we will have Jg plus md square. So now for rod, so J equivalent, then for rod it will be Jg, which is a 12, 1 over 12. Mass of the rod is m, and then the total length of the rod is, in this case, is L squared plus md squared. So m into d. So d here is L over 2. So L over 2 squared. So this one, this one, this is for the rod. So this one is for rod, or sorry, this one is for bar. And then for bob, so the bob is the moment of inertia of a sphere. So having mass and radius r about its center of mass is 2 by 5 mr squared. But here, this bob is not rotating about its center, but then what we will consider, we are going to consider that this mass is attached to a virtual rod, like the moment of inertia of mass m attached at the end of light rod having length L, that is ml squared. What I am assuming here, that this mass is attached at the end of the rod L, and here that rod is a virtual rod. So then for bob, we'll have here m L squared. So it is plus uppercase M L squared. So J equivalent is now 1 over 12 ml squared plus a quarter ml squared plus uppercase M L squared. So now I have it J equivalent in this a third M L squared plus uppercase M L squared, and then I can take that and as a common factor, it will be a third m lowercase m plus uppercase m into L squared. And I got that G equivalent, and I'm going to simplify it. Now the sine theta can be written as theta. So from here I get minus half mg theta L, and from here it is minus m uppercase m g theta into L, and J equivalent is a third lowercase m plus uppercase M L squared. Now, uh, I can take L as a common factor from here, and it's going to be cancelled with this L squared. So, and then I can take at G as common factor, so it is minus G L, and then theta as a common factor. So minus G theta half M plus uppercase M is equal to one third lowercase m plus M L squared. So then here L is going to cancel with L squared. So we'll have minus G theta half M plus M is equal to a third lowercase m plus M L theta double dot, and then I can rearrange that. And after rearranging, a third M plus uppercase M L theta double dot plus half M plus M uppercase M G theta L. So now here, so this one and these two factors. So natural frequency is equal to the coefficient with theta kt divided by the coefficient with theta double dot. So in this case, you'll have a natural frequency as half lowercase m plus uppercase M into G over a third lowercase m plus uppercase M into L under the radical. So that is the natural frequency of the system, which is shown here. So for 2.71, so that is the natural frequency. Thank you very much for watching.